This is chapter 16, video 2, and we are going to review this tiny bit before we move forward in your notes, so please pull out your notes. I wanted to point out again, these are the acids and bases you need to memorize, and these are found in the Quizlet. So make sure you spend lots of time on the Quizlet. I may assign them at some point. Notice that the acids have hydrogens in the front, and remember that the hydrogen ion is a proton, because a hydrogen atom only has a proton, one proton, and one electron orbiting it. And if it loses that one electron, all that's left is the proton. And we went from being a neutral hydrogen atom to losing the electron. Let me write it over here like this. The hydrogen atom losing the electron and becoming an ion, just the hydrogen ion. That's the proton. Okay? The strong bases have the OH groups in them. The hydroxide ion, OH minus, is the hydroxide ion. You need to make sure you know that. And it has strong metals. It has metals, lithium, sodium, potassium, calcium, strontium, and barium in them. So you do need to memorize those from the Quizlet. Remember, we went through different definitions. We had the Arrhenius model that was aqueous only in water, and it releases hydrogen ions, H pluses. And then you have the base, which release OH hydroxide ions, and so that's why we have all these hydroxides over here. Then we had the Bronsted-Lowry model. This one was super important. And here, acids are proton donors, and bases are proton acceptors. And if you donate a proton, you're deprotonated, you lose it. If you accept the proton, you're protonated, you gain it. Okay, then we made conjugate acid-base pairs, and we will review those together in class. Then we had the Lewis model, which is kind of the one that's kind of the most difficult to figure out, but the acids are kind of the opposite. In the Bronsted-Lowry, acids are proton donors. In the Lewis models, acids are the opposite of proton is electron, and last a donate is accept. So they're electron acceptors. And in the Bronsted-Lowry model, bases are proton acceptors. In the Lewis model, bases are the opposite of protons is electrons, and the opposite of accepting is donate. So that's the Lewis model. And then we have this you really need to know, is that the Bronsted-Lowry model is a subset of the Lewis model, and the Arrhenius model is a subset of the Bronsted-Lowry model. So the least amount of things are defined as acids and bases here. More things are defined as acids and bases here, and the most things are defined as acids and bases in the Lewis model. And we will also review some of that. And that moves us on to the self-ionization of water. Water can react with itself to form ions. Remember, hydrogen ion, that's a cat ion. Ions are things that have charges. The hydroxide ion is an anion, a negative ion, and it has a negative charge. And it's because they either have lost or gained electrons. If they lose an electron, they're a cat ion, and if they gain an electron, they're an anion, because electrons are negative themselves. So if you put an extra negative in, you get a negative value. If you take a negative away, you get a positive value. This is all from a long time ago that we need to review it really quickly. So water can make ions of itself. So here we have a hydrogen ion, which is really going to be a proton, and protons are positive, right? Getting attracted. Remember, water molecule has a negative side and a positive side because it's polar. So the positive proton is attracted to the negative side because opposites attract. And when it does that, if you have left, this stuff that's left, that's the hydroxide ion. That's the OH minus. And this is the hydronium ion, OH3 plus. So this is what happens when water ionizes itself. We have two water molecules, and they form OH3 plus, H3O plus rather, and OH minus. So here is again the self-ionization of water, and this is just a picture of how it's happening as well. Okay, one of these hydrogens is going to come and be attracted to those electrons right there, and that's what happens, and you have left over just the hydroxide ion. But let's write the equilibrium constant for this. Remember that the equilibrium constant is the products divided by the reactants. And we just learned about that in the previous chapter. So what's the equilibrium constant for this? Well, it would be the products of H3O plus times OH minus divided by the reactants of H2O squared. But then we have to simplify it. And anything with an S for solid or an L for pure liquid, the concentration of any one of those things is a 1. So we have a liquid right here. So this becomes a 1. So the only thing left over is this top part. So the equilibrium constant is just really the hydronium ion concentration times the hydroxide ion concentration. Now, this is an equilibrium constant for that reaction, but because it's dealing with water, it gets a special name, and that's all that is. The ionization constant of water, the Kw. It's the equilibrium constant of water. It's a special name for what you've already done. So the Kw is equal to the hydronium ion concentration times the hydroxide ion concentration. Make sure you're filling in your notes, okay? Alright, in pure water, the concentration of the hydronium ion and the hydroxide ion are both 1 times 10 to the minus 7. So, if I put this value into the formula, that's what I get down here. 1 times 10 to the minus 7 times 1 times 10 to the minus 7, I get 1 times 10 to the minus 14. So the Kw is always 1 times 10 to the minus 14 at 25 degrees Celsius, or the standard temperature. Okay, so whether a solution is an acid, a base, or neutral, the hydronium ion concentration times the hydroxide ion concentration is always equal to this. Okay, so let's use that formula. This is sort of a formula to solve this next question. The concentration of hydronium ions, we've got to memorize those, in an acid is found to be 5 times 10 to the minus 7 moles per liter. What is moles per liter? Moles per liter is molarity, capital M. We have that before too. So what's the concentration of the hydroxide ions? Well, we use the formula that the hydronium ion concentration times the hydroxide ion concentration is always equal to 1 times 10 to the minus 14. Then, and we know that here the concentration of hydronium ion is 5 times 10 to the minus 7. So now all we have to do is divide both sides by 5 times 10 to the minus 7. So that the hydroxide ion concentration is equal to 1 times 10 to the minus 14 divided by 5 times 10 to the minus 7. So I'm going to pull up my calculator and put that in. Alright, put it on. So it's 1.0 second function dE negative 14 enter divided by 5 second function dE, oops, go back one, second function, and let's not hit the second function. Second function dE negative 7 enter. So it's 2 times 10 to the minus 8. 2 times 10 to the minus 8 molar. Because the concentration is going to be in molarity. Molarity. 2 times 10 to the minus 8 molar. Alright, that's an easy one to use if you use the formula, this formula right here. Just plug in what you don't know and solve for what's asked. Now the pH scale is the negative logarithm of the hydronium ion concentration, H3O plus. You could also say, or the hydrogen ion concentration. And we can only say that because water ionizes itself. So when we make hydrogen ions or hydronium ions, they can refer to it in both ways. So it's the negative logarithm of the hydronium ion concentration. I don't expect you to have to remember how to do the logarithms. This is just to remind those of you who've seen it before. But all you really need to do is put it in your calculator. And I'll show you how to do that. Switch it over. all we need to do is put negative logarithm of that number. So when we come down to a practice problem, we'll do that. So in pure water, the negative logarithm of the hydronium ion concentration is the negative logarithm of 1 times 10 to the minus 7. Now, I told you, right up here, that in pure water, the hydronium ion concentration is 1 times 10 to the minus 7. So that's all this is. So when I put that in, I get a 7 in the calculator. Now, let's prove it. So, I want the negative log. So negative, this little negative sign. There's the logarithm function right there. Log, and then 1, second function, negative 7, close parentheses, enter. It's a 7, okay? That's the number. Now, if the number right here is a 1, then this number here is going to be identical to the exponent, but it's going to be, since it's the negative of the exponent, if the exponent is negative, it's going to be positive. If the exponent is positive, it will be negative. Alright, so here, pure water has a pH of 7 right there. Now, anything that's less than 7 is going to be an acid, and anything that's greater than 7 is going to be a base. So, blood has a pH that's greater than 7, so it's very slightly basic. Coffee is acidic, orange juice is acidic, your gastric juices in your stomach, very acidic. So, notice that the pH scale ranges from 0 to 14. The higher the number, the more closely it is to a base. The lower the number, the more close it is to an acid. The stronger and stronger the acid. So let's try this next one. The hydronium ion, H3O+, concentration in a shampoo is this molarity. What's the pH? Well, pH equals the negative logarithm of the hydronium ion concentration. It's one of the formulas on your reference chart that you're going to get. So, negative logarithm of 2.0 times 10 to the minus 5. So let's put it in the calculator. Negative logarithm 2.0 second function negative 5 close parentheses enter. So I got 4.7. This has a pH of 4.7. Where does that fall on the pH scale? Well, 4.7 is down here somewhere. So this is an acidic shampoo. The pH of that shampoo is closer to the acid side than the base side. Alright, so let's keep going. Remember, all the formulas that I'm using will be on your reference sheet, and you will use them easily. This will become something that's not too hard to read at all. What is the pH of an aqueous solution that has 4.4 grams of hydrogen iodide dissolved in 500 milliliters of water? Now, pH is the negative logarithm of the hydronium ion concentration. Well, we don't know the hydronium ion concentration. Remember, the concentration is in moles per liter, or molarity. We have to figure out the molarity. We have hydrogen iodide, and it falls apart into the hydrogen ions and the iodine ions. We got to figure out how many moles of hydrogen iodide do we have. So we take the 0.400 grams, and we have to come in the moles using the molar mass. So I always go and look it up, and hydrogen is 1.01, and iodine is 126.9. Add them together, we get 127.91 grams per mole. That's the molar mass. So we're going to turn our grams of hydrogen iodide into moles using the molar mass, like we've done a million times at this point. Grams cancel. And so how many moles is that? We have 0.4 divided by 127.91. I get 0.0031 precipitate. 0.0031. That's how many moles I have. Okay? So that's the number of moles In order to figure out molarity, I needed moles over liters. So it's 0.0031 moles. Now, what about liters? I have 500 milliliters. You need to remember how to convert milliliters. I'm just going to write it up here because of room. You have 500 milliliters. Remember, there are 1,000 milliliters in 1 liter. This is just a basic unit conversion. So it's 0.500 liters. So 0.500 liters. So the molarity of this solution is 0.0031 divided by 0.5. So 0.0031 divided by 0.5. That gives you 0.0062. 0.0062. 0.0062 molar. Okay? So let's put that into the formula. It's the negative logarithm of 0.00062. And that's going to give me the pH of this solution. So negative log of 0.0062, close parentheses, is 2.2. The pH of this solution is 2.2. Now, the only thing that made this one more complicated is you had to turn mass into moles using the molar mass. And you had to turn milliliters into liters, and then you divide it out, moles per liter, to get the molarity. Okay? And you want to know the molarity. The molarity is the concentration. Alright. The pOH scale. The pOH scale and the pH scale are very closely related by this formula. pH plus pOH is 14. pH kind of means the power of hydrogen, and so this might be the power of hydroxide. The pOH scale is the negative logarithm of the hydroxide ion. The pH is the negative logarithm of the hydronium ion, or the hydrogen ion. The pOH is the negative logarithm of the hydroxide ion. Right, the concentration of the hydronium ion is 10 to the negative pH. The concentration of the hydroxide ion is 10 to the negative pOH. All of these are easy formulas to use. We will play with them and use them a lot in practice, okay? So let's do this one. We have 0.10 molar hydrochloric acid, HCl, one of the ones you need to memorize. It has a hydronium ion, H3O plus, concentration of 1 times 10 to the minus 1. It has a calculate the pH, the hydroxide ion concentration, and the pOH. I'm going to write down all the formulas that we know. We know that pH is the negative logarithm of the hydronium ion, or the hydrogen ion concentration. We know that pOH is the negative logarithm of the hydroxide ion concentration. We know that pH plus pOH is 14. We know the concentration of the hydronium ion is equal to the 10 to the negative pH. We know the concentration of the hydroxide ion is equal to 10 to the negative pOH. All of these formulas we will have. So what did they tell us here? They told us the concentration of the acid. Okay, so this is hydrochloric acid. Then it falls apart or dissociates into 1 hydrogen and 1 fluorine. So if I have 0.10 moles of this, that's 1 hydrogen. It's a 1-to-1 ratio. I would have 0.10 moles of hydrogen, or the hydronium ion. Remember, the hydrogen ion, immediately sticks itself to water to make the hydronium ion. So this concentration can be used here. The pH is also the negative logarithm of the hydrogen ion concentration. So to calculate the pH then, the pH is going to be the negative log of 0.10 moles. So what's that? Negative log of 0.10 moles. And that's just the number 1. Negative log of 0.10 moles is 1. pH is 1. Okay, so calculating pH, done. What about the pOH? Well, remember that pH plus pOH equals 14. So 1 plus pOH is 14, so the pOH is 13. Alright, did that. Hydroxide ion concentration. Well, that's this one. So the concentration of the hydroxide ion is equal to 10 to the negative pOH. So it's 10 to the negative 13. So I put that in the calculator. It's just going to say 1 times 10 to the negative 13. I'll show you 10 up here, negative 13, enter. It's just 1 times 10 to the negative 13. So the concentration of the hydroxide ion is 1 times 10 to the negative 13. And that's all of that question. And all of this is taking one thing that we know, and then once I know one thing, I'm able to figure out all the other things. Let's keep trying. A sulfuric acid solution has a hydronium ion, which concentration of this. So we know that pH is the negative log of the hydronium ion. We know that pOH is the negative log of the hydroxide ion. We know that pH plus pOH is 14. We know the concentration of the hydronium ion is 10 to the negative pH, and the concentration of the hydroxide ion is 10 to the negative pOH. All the formulas on your reference book. So, let's look at it. Here's the hydronium ion concentration. What do I have then? I already have this thing right here. Okay? That means I can calculate the pOH. pOH is a negative log of the hydronium ion concentration. So it's the negative log of 3.2 times 10 to the minus 2. So let's put that in our calculator and see what number we get. Negative log 3.2, second function, EE, negative 2, close parentheses, enter. So I get 1.5, so that the answer is 1.5. The pOH is 1.5, okay? Alright, now that I know the pOH of 1.5, I can use this formula. I just figured out this. So I now can figure out the point of pH. So pH plus pOH equals 14. I just figured out that pOH is 1.5. So I just have to subtract 1.5 from both sides. So what's 14 minus 1.5? And because I'm don't trust myself, I put it in the calculator. 12.5. Alright. pH is 12.5. Okay? And now I just figured out, I have figured out the pOH. And I figured out the pH. And now I'm going to figure out the hydroxide ion concentration. Well, the hydroxide ion is, oh, I just realized I wrote the wrong thing. This is hydronium, H3O+. Alright, so I gotta go back and do, this is not the pOH, this is the pH. So, H3O+. I didn't want to do that. So it's still, so instead of this being pOH, this is pH. So, I'm going to erase this real quick and correct it. Sorry about that. Ooh, the class is yelling at me. There you go. So the hydronium ion concentration is this. Alright, so now we know the pH is 1.5. So that means that the pOH is 12.5. Alright, so we figured out pOH, we figured out pH. Now we can figure out hydroxide ion concentration. The OH minus. Don't forget, hydronium is H3O+. Hydroxide is OH minus. See how easy it is to get mixed up? Don't follow that example. You go straight. So what is the hydroxide ion concentration? There's hydroxide ion. So the hydroxide ion concentration is 10 to to the negative pOH. So it's 10 to the negative 12.5. You need to put that in your calculator because that's going to be something that you don't expect. So 10, up here, negative 12.5. Enter. 3.2 times 10 minus 13, or 3.16 times 10 minus 13. 3.16 times 10 to minus 13 molarity is the hydroxide ion concentration. So that was the last thing it asked for. Again, it used these formulas. The only thing I did wrong is I got that. You got to make sure that is what you're looking at when they ask hydronium ion. Okay? So hopefully you follow me on that. We will pick up with the acid-base strength in the next session.